Welcome to the course of HDL Digital Circuit Design. Today's topic is Programmable Logic Array. I'll be explaining how to program particular combination logic in PLA and its limitation and advantages. Myself Shilpa Kedar Rudravar, Assistant Professor, School of ENTC Engineering, MIT Academy of Engineering, Alandi, Pune. So moving ahead with the topic Programmable Logic Array. So in the previous section, we have seen what is meant by PLD, Programmable Logic Devices, which is an IC containing large number of gates flip-flops which can be configured by the user to perform different functions, and it is a single IC on which you are implementing digital logic. And here there are programmable devices which can be programmed using programming software or programming process. So here you are able to see on the left hand side, this diagram indicates that PLD is there, in which you are having logic gates and programmable switches. Inputs will be given to the input side, and depending upon logic you are implementing, that will be programmed by making switches on and off, and that way you will be getting your output, that is function over here at the output side. Now there are different types of PLD as we have seen in the previous lecture, that is programmable array logic, programmable logic array, and PRON. Basic logic device over here is the AND array and OR array. Depending upon which is programmable and which is fixed, or both are programmable, depending upon that we are defining which type of PLDs are that. So over here you are able to see that is yellow indicates fixed array logic and blue color indicates the programmable one. So when AND array is fixed and OR array is programmable, then it is a programmable read-only memory. That is one type of PLD. Second, you are able to see that AND array is programmable and OR array is fixed. At that time, that particular PLD is programmable array logic. And when both are programmable, as you are able to see green color or blue color, whatever you are able to see, so that is both are programmable, that you are able to program AND array as well as OR array, then it is called as a PLA. Now we are starting with the PLA, programmable array, programmable logic array. Here you are able to see this is AND array and this is OR array. In PLA both are programmable, and that's why it is shown by this color. Here input to the AND array are shown by the N inputs. So here there might be multiple input present. Each input can be inverted. So if I am giving input A, B and C, so I am able to generate A bar, B bar, C bar also because of inverter present. So these are what are the number of inputs to the AND gate. Now it will be generating K product terms over here, and that output will be given to the OR gate. So number of OR gate will depend upon number of functions you require. So here I will be explaining these things using this boolean function. Suppose you need to implement this boolean function, means I am having function W, X and Y. So there are three functions, that is 3 output I require. That's why I require 3 OR gate over here. So array of OR gate will be having 3 input over there for the OR. Next over here we are having how many product terms? So 1, 2, 3, 4, 5, 6, 7. That way I'll be requiring 7 AND gates over here because I require 7 product terms. Now when I am giving A, B, C, D over here, because A, B, C and D, these are the inputs available, because of this inverter it will be generating A bar, B bar, C bar, D bar also. So whenever in the product terms I require complement of C, complement of D, that is inverted D, so it will be possible using this inverter. Once that product terms are getting generated, that will be given to the OR input over here. So for generating W function over here, I require to apply this product terms over here. So product term generated from this particular AND gate will be given to this, and one input of OR gate, and second product term will be given to the second input of OR gate, and that way this will be the function W. In the same way I will be generating X and Y. So I require total 3 OR gate at the output side or in our array. So hope the things are clear. Now one question is over here, that why this XOR gate is shown, because this is the OR gate, and this I told you that depending upon function you will be having that many OR gates over there, but here you are able to see the XOR gate. Now what is the role of this XOR gate? Now as this is the PLD, which is over here it's the PLA, sometimes you require the inverted logic at the output side. There should not be any requirement of NOT gate IC for inverting that logic, and that's why this inversion is provided using this XOR gate. Now here for your reference I have shown truth table of XOR gate, where 0 0 gives the output 0, 0 1 gives the output 1, 1 0 gives the output 1, and 1 1 is for 1 1 output is 1. Sorry, 0. So 0 1 1 0, you are able to see it or not, I'm not that way sure. So over here, so you are able to see 1 1, output is 0. So now just check, if my output is over here and I want that to be inverted, so I need to connect one terminal of this XOR gate to the logic 1, so that whatever data I am getting over here will get inverted. Now how that is possible? So over here you are able to see when one of the input of your XOR gate is 0, connected fixed to the 0, output you will be getting depending upon whatever present on the second terminal. That is, if 0 is present you will be getting 0, and 1 is given, then you will be getting 1. So consider the same logic over here. If I have connected one input of XOR gate to the 0, that is over here, suppose this is 0 and this link is closed, so I have connected it to the 0, meaning of that whatever coming on the second terminal, that here it is mentioned by B, so same output you will be getting over here. So if I am having 1 over here, I'll be getting 1, so there will not be inverted output. But if I want my logic to be inverted, that is my requirement, and don't want to use extra NOT gate over there, so that will be done through this XOR gate. Now suppose I am connecting one of the terminal to logic 1, one of the terminal of this XOR gate to logic 1. So see over here, you are having 1 connected to one of the terminal, so whatever present on the second input will get inverted at the output. So if 0 is given, 1 you will be getting, when 1 is given, 0 you will be getting. So here you are able to see same thing. If 1 is connected to the one terminal of XOR gate, then whatever data you are getting over here, that is getting inverted at this particular time output, so that there is no need of extra NOT gate connection. Hope the things are clear to you. Moving ahead with the next slide. Now if you want to implement any logic, digital logic using PLA, so how to implement it? So for that I have taken one example. Here you are able to see that one truth table has been given. Inputs are A, B, C, and two functions are there, F1 and F2. Now as there are 3 inputs, there are total 8 possibilities, that is 0 0 0 to 1 1 1, and depending upon that you are able to see these outputs are present. Now whenever truth table is given and whenever you need to have an equation out of that, you need to solve it using K-map, and hope the K-map concept is already you know in the first year itself, but just for your understanding I'll be briefing in short. So here as there are 8 options available, so you need to have a block of 8 over here, 2 by 4 over here. So whatever is the MSB you need to write it over here, 0 1, and whatever is the LSB bits are there, BC, you need to write here. As there is only one variable, options are 0 and 1. As there are two variables, options are 0 0 0 1, 1 0 and 1 1. Here you are using gray coding. That is, after 0 1 I am not writing 1 0, I am writing 1 1, because if I am writing it near to this 0 1 and 1 0, both will get cancelled, and that's why your equation will not be proper, and that's why you need to use binary coding over here, gray code over here. Now how to solve it? As you know that A is the MSB and B and C are the least significant bits over there. So 0 0 0 for how many functions you are having, that many K-maps you need to draw. So there are two functions F1 and F2, that's why there are two K-maps has been drawn. So here 0 0 0 indicates this 0, B is also 0 and C is also 0, means this particular block will be 0. Again 0 0 1, then this is 1. 0 1 1, this is 3. 0 1 0, that is in binary. 0 1 0, in decimal it is 2. Likewise you need to write at the corner the number of that block, so that it will be easy for you to put that outputs over there. So this is 0, 1, 2, 3, 4, 5, 6 and 7. Just do it by your own and just see whether it is coming same or not. So according to this, I'll be writing F1 output over here. So 0, 0, 0 output is 1. That's why in this box it is written 1, because this is the 0th block. First block you are having 1, again it has been written like that. For 2 it is 1, and this is 3 because of gray code, and this is 2, that's why it is 1. That way you need to fill up this particular blocks over there, and then you need to apply the grouping rules over there. So you can make this as a one group, you can make this as a one group, and you can make this and this as a one group. Whenever you are solving, you need to solve in this way. I'll be explaining this particular part over here. What is the equation for this? That is 1 1. If I am grouping this 1 1, so 0 and 1, that is A is 0, A is 1, so that is getting cancelled, and you are having 0 0, that is B bar and C bar. So that's why this particular equation in which you are getting B bar and C bar. Plus, because this equation has been solved, this grouping has been solved, then solve this grouping. Now here A is what? 0. 0 means A bar, and here 0 0 and 0 1, where 0 0 is constant, but this 0 is changing with 1, and that's why C is changing from 0 to 1. So whatever is changing, just remove that, and whatever is the constant you need to take it, that is B bar. So A bar and B bar, this is what is your this answer of this particular group. Then solve this and this in same way, you will be getting A bar, C bar. Now if you want to complement, you can complement. If you want to leave it like that, just leave it. So I'll be telling you why they have taken like this over there. Now same way you need to solve F2, and after solving you are getting F2 as a AB plus AC plus A bar, B bar, C bar. Why you are getting A bar, B bar, C bar? Because there is no group form for this. This is the single digit you are having. There is no grouping possible, and that's why this is A bar, B bar, C bar, because 0 0 0, and that's why it is coming in 3 bits over there. Now you need to try to reduce the implementation as far as possible. So over here, if I am taking this equation and this equation, so number of product terms are 1 2 3 4 5 6. But if I am taking complement of this, which is over here, F1 bar is written, so A bar, B bar is written as a AB, A bar, C bar is written as a AC, B bar, C bar is written as a BC. So in this equation and in this equation, you are able to see AB and AC are common, and that way you are reducing two AND gates over there, and that is very much required to optimize the circuit. So here final output you are able to see AB plus AC plus BC, and this is the second one. Now moving ahead with this thing. Now as you have got this particular thing, out of which two are common, and that's why it is taken once, and that's why total product terms required are 1 2 3 and 4. Over here you are able to see AND array and this OR array, both are programmable, and that's why we are making the cross connections over here by this way. So both are programmable. If that is dot, it is fixed. Now as I told you, at the input side you are giving A as well as its complement. So this is shown by this particular figure or symbol, and depending upon your product A, B, so I'll be taking this A and this B over here, and I'll be shorting this A short, this B short, means this is my AB. So it is written over here same way AC, same way BC, and same way A bar, B bar, C. And that way over here for F1 I required AB, AC and A bar, B bar, C. So it is given to the one OR gate, and second it has been given to the second OR gate. Now so whatever function you want to complement, that way you need to program this XOR gate. So if you want to invert, then connect one of the terminal of XOR gate with 1, and if you want to give as it is, then connect it with the 0, and rest of the input you need to connect the output of this OR gate. So that way complement function is possible over here. Now we have seen how to implement combination logic using PLA. So what are the limitations of this particular PLA? So you are able to see The first limitation is complexity and cost. That is, PLAs can be complex and costly to manufacture due to large number of programmable links, because you need to program all AND array links and all OR array. That's why it is somewhat large number of links you need to program, so it is somewhat complex and costly. Second point, that is the speed. The multiple level of logic within the PLA can introduce delays, making them slower compared to the some of the types, some of these PLDs, that is FPGA, PAL over there. So as you are programming all AND array and all OR array, so somewhat speed limitation will be there. It will not be that way faster, but it will be making it somewhat slower. Third point, that is the power consumption. The dense interconnection of logic gates can result in higher power consumption, which might not be suitable for low power application. So because of density over here, the power consumption will be more. Next is scalability. PLA may not be easily scaled for very large designs, especially when compared to more advanced programmable devices like FPGA. So you are not able to scale it as far as the FPGA, which is used for implementing complex logic. So that is the next limitation. Now what are the advantages? First advantages you are able to see, that is flexibility in logic implementation. As both the arrays and OR are programmable, so flexibility is very high over there. So you are able to program both the arrays. Then customization over here, that is second point. User can customize the logic design to meet specific requirements, making PLA suitable for a wide range of application. So over here customization is possible because you are able to program both the arrays. Compact design. PLA allows for the implementation of multiple logic functions within a single device, reducing the need of multiple discrete ICs, because inverting also is done in PLA only itself only. So that's why no need to have no need to use different ICs. So compact design is possible. Next is high integration. They offers a high degree of integration, enabling the design of complex digital systems on a single chip. That is, integration means you are integrating everything on a single chip. And last one, simplified design process. The programmability of that AND and OR array simplifies the design process, and this is what is the limitation and advantages of PLA. Hope the things are clear to you, and I have explained it using one example implementation also. So thank you everyone. We'll meet in next session. So thank you. Happy learning.